The program introduces regression analysis as a statistical method used to examine relationships between dependent and independent variables. Regression analysis is fundamental in finance because it helps analysts identify patterns, estimate sensitivities, and forecast future outcomes. The program explains that the simplest regression model expresses the expected value of a dependent variable as a linear function of one explanatory variable. This relationship is represented by an intercept term and a slope coefficient, where the slope measures the expected change in the dependent variable resulting from a one-unit change in the independent variable. Regression models are widely applied in asset pricing, portfolio management, and risk forecasting. The program emphasizes that regression analysis is not limited to identifying correlations but is intended to quantify predictive relationships between variables. The error term in the regression equation captures influences not explained by the model's independent variables. This residual component reflects omitted factors, random shocks, or measurement errors. In financial applications, residual risk may arise from unexpected market events, economic announcements, or firm-specific developments. The topic also explains that regression models are considered linear when they are linear in their parameters, even if variables themselves undergo transformations. Understanding this distinction is important because many financial relationships require logarithmic or nonlinear transformations while still remaining compatible with linear regression techniques. Topic focuses on ordinary least squares, OLS estimation, the most common method used to estimate regression coefficients. OLS determines the regression line by minimizing the sum of squared residuals between observed and predicted values. The program explains that OLS estimators are unbiased and consistent under specific assumptions, making them highly useful for empirical financial analysis. Analysts rely on OLS because it produces coefficient estimates that best fit the observed data according to the least squares criterion. In practical finance, OLS estimation is used to evaluate portfolio betas, estimate risk exposures, model interest rate sensitivity, and examine economic relationships that influence investment and risk management decisions. The program also outlines the core assumptions underlying the classical linear regression model. These assumptions include independence and identical distribution of observations, zero conditional mean of the error term, constant variance of residuals, and sufficient variation in the explanatory variable. Collectively, these assumptions ensure that OLS estimators possess desirable statistical properties and that hypothesis tests remain valid. Violations of these assumptions may produce biased estimates or unreliable inferences. For example, heteroskedasticity and autocorrelation are common problems in financial datasets that can distort regression results. Risk managers must therefore evaluate whether model assumptions hold before relying on regression outputs for forecasting or decision-making purposes. Another important topic is the interpretation of regression coefficients and measures of model fit. The slope coefficient measures the expected change in the dependent variable associated with a one-unit change in the independent variable, while the intercept represents the estimated value of the dependent variable when the explanatory variable equals 0. The program also introduces the coefficient of determination, or R superscript 2, which measures the proportion of variation in the dependent variable explained by the regression model. Higher R superscript 2 values generally indicate stronger explanatory power. In finance, R superscript 2 is widely used to evaluate the effectiveness of factor models, benchmark tracking strategies, and predictive relationships between macroeconomic variables and asset returns. Topic introduces hypothesis testing within the regression framework. Analysts often need to determine whether estimated coefficients are statistically different from hypothesized values, commonly 0. The program explains that hypothesis testing uses t-statistics and critical values derived from the student's t-distribution. If the calculated t-statistic exceeds the critical value, the null hypothesis is rejected, indicating statistical significance. Confidence intervals and p-values provide additional methods for evaluating coefficient reliability. In finance, regression hypothesis testing is essential because analysts must determine whether observed relationships between variables are meaningful or simply the result of random variation. Reliable inference supports stronger investment analysis, economic forecasting, and quantitative risk management. Overall, topics establish regression analysis as one of the most powerful quantitative tools in modern finance and risk management. The program demonstrates how regression models allow analysts to estimate relationships, forecast outcomes, and test financial theories using empirical data. OLS estimation provides an efficient method for fitting regression models, while hypothesis testing enables analysts to assess the reliability and significance of estimated coefficients. These concepts are fundamental in portfolio management, derivatives pricing, factor investing, and enterprise risk analysis. By understanding regression techniques and their assumptions, candidates gain practical analytical skills necessary for interpreting financial data and supporting evidence-based decision-making in complex market environments.